So we're going to take into account what we learned from a variety of sections, in particular 4.5 and 4.6 about shapes and limits with infinity, which relate to the end behavior on graphs. And to do that, we need to look at the first derivative test, second derivative test, and then take some limits. But before we do any of that, we really ought to know the domain of the function that we're working with here. So it's a rational function. So if the denominator is 0, and I can pretty clearly see if somebody plugs in 2, we're going to get a 0 in the bottom. So as far as the domain here, it's everything but 2. So in interval notation, I could write negative infinity to 2 union 2 to infinity. So anything but 2 is okay. Now, it could be that would lead to a hole in the graph if x minus 2 is also a factor of the top. So the question is, what happens when we actually plug in 2? Do we get 0 top and bottom? So we could plug in 2 and check that. That would be pretty easy. But I want to try and factor the top just for fun. Does 2x squared plus x minus 3 factor? So we can guess at this. 2x squared has to be 2x times x, and 3 has to be 1 times 3. And so the question is, does the 3 go here or there? And I'm going to guess it goes here, and that's a 1. And this is negative. I'm going to put the negative there and the positive there. So then the middle term is questionable. So let's see, the middle term is going to come from 3x minus 2x, which is x. So yeah, it does factor as this right here. And notice that neither of those factors is x minus 2. So at x equals 2, we don't have a hole. What it looks like is at x equals 2, we have a vertical asymptote. And we'll take a limit to check that in a moment. Question mark, check with limit. So we'll come back to that. Now that I know the domain, I want to take the derivative. So f prime, we're going to have to use the quotient rule here. Let's see, is there an alternative to the quotient rule? Sort of, we'll look at that in a minute. All right, quotient rule says take the derivative of the top first. The derivative of the numerator is 2 times 2 or 4x. Derivative of x is 1 times the denominator, x minus 1. And then subtract, leave the numerator alone, 2x squared plus x minus 3, and multiply by the derivative of the denominator, which is 1. All of that is divided by x minus 2 squared. And we got to do a little algebra to clean that sucker up. We have to distribute here. So boom, boom, we're going to get a 4x squared. And then we're going to get a minus 8x and then plus 1x. So that's going to be a minus 7x and then minus 2. And then we're subtracting all of that second one. So be careful with your negative and positives there. So that's going to be minus 2x squared minus x plus 3. And again, since that was a 1 out there, I didn't have to do anything with that, but otherwise we'd have to distribute that too if it wasn't just a 1. All of that is over x minus 2 squared. And we have some like terms there, so let's clean that up. So 4x squared minus 2x squared is I get a 2x squared in the top. Negative 7x minus x, we get a negative 8x. And then negative 2 plus 3 would be a plus 1 over x minus 2 squared. And then the first derivative test says, look for any place that either this is equal to 0 or any place this does not exist. And remember, the does not exist means it doesn't exist here, but it does exist in the original function. And here I can see in the denominator that x equals 2 is a problem, again, but it ain't in the domain, so I don't care. So I only need to consider when it's 0. The only time it's going to be 0 is if the numerator is 0, so we have to solve that. When does 2x squared minus 8x plus 1 equals 0? And I can tell that ain't going to factor, and so our only choice here is quadratic formula or complete the square. I'm going to use the quadratic formula. So we get opposite of b, so that would be 8 plus or minus the square root of negative 8 squared, 64, minus 4 times 2 times 1. So that'd be 64 minus 8 all over 2 times 2. 64 minus 8, I think, is 56 on a good day. That looks right. All over 4. And let's see, does this clean up at all? If we try to factor 56, 56 is that 7 times 8? Yep. And 8 is 2 times 4. So I can take the square root of 4 here. So this would be 8 plus or minus 2. 7 times 2 is 14, still in the square root, over 4, and everything divides by 2. So 4 plus or minus the square root of 14 over 2. So I have 2 critical numbers, and we need to figure those out on a calculator. So I'm going to do that on the side here. So we've got 4 plus the square root of 14 over 2, and that gives me about 3.87. So I'm getting about 3.87. And then the negative one is 0.13-ish. So these are my critical values, critical numbers. So the next thing is, do these lead to maxes or mins? And so we got to do a little number line analysis of that. Before I do that, I think I'm going to find the second derivative. And the cleanest version of the derivative we have would be this one here. So we'll take the derivative of that next. So 2x squared minus 8x plus 1. So we have the original function. Oops, let's use different color. F of x is equal to 2x squared plus x minus 3 over x minus 2. We've got the derivative of that as 2x squared minus 8x plus 1 over x minus 2 squared. Double check I did that right. Looks good. Now we need the second derivative, which is the derivative of the first derivative. All right, so derivative of the numerator of the first derivative, 2 times 2 is 4x minus 8 times the bottom, x minus 2 squared. And then we have a minus the derivative of the bottom. And so the derivative of something to the power 2 is 2 times that something to the power 1. And then multiply by the derivative of the inside, the derivative of x minus 2 is just 1. So that right there is the derivative of the bottom. Times the top. 2x squared minus 8x plus 1. And all of that is over the denominator squared. The square of a square is a 4th power. Okay, cleaning this up. I don't want to square this out, but please notice that on each side of this subtraction right there, we have a factor of x minus 2 that we can pull out. And that'll make this a little easier to work with. So from the numerator, I'm going to pull out an x minus 2. And then what's left? So I took one of these, so I have a 4x minus 8. And there's still an x minus 2 there because I took 1 from that square there. And then otherwise I have minus 2. I took all of that out right there, that x minus 2 out front. And then I have the 2x squared minus 8x plus 1. And all of that is over that x minus 2 to the 4th power. So this is fun because now this x minus 2 cancels with one of those, giving me a 3rd power down there. So that was nice. And that's pretty typical with second derivatives of rational functions. All right, we're going to distribute this stuff out here. And we're going to distribute the -2 and then clean it up. So what do we get? We get 4x squared. And then we're going to get a -8x and another -8x. So -16x. Negative times negative is a +16. And then distributing the -2 here, we're going to get -4x squared plus 2 times 8 is 16x, and -2 times 1 is -2. And ooh, lots of stuff cancels there. So this is over x minus 2 cubed. So we've got the 4x squared minus 4x squared, ta-ta. -16x plus 16x, goodbye. And then we have a 16 minus 2, which is 14. Wow, 14 over x minus 2 cubed. All right, let's make sure I didn't make any errors. That looks too good to be true, but maybe not. Derivative of the numerator looks good. Derivative of the denominator. Factor, did I do the multiplication right here? 4 times 2 is 8, negative, -8, -16. Yeah, that looks right. 2 times, 2 times, 2 times, change the sign. Oh, that looks okay. That looks like the second derivative. And we want to know, is this equal to 0 anywhere? And the denominator can't be 0, 14 can't be 0, so the answer is no, that can't happen. And then the other question is, does this not exist anywhere? And it does not exist if x is 2. All right, now, this can't be an inflection point, but it could mark a change in concavity, right? The function doesn't exist at 2, but might this be a change in concavity? All right, so I'm going to do my number line analysis, and then we'll take some limits at infinity. Oop, I don't want to do it on page yet. I can do that here. So let's get me a number line. And first, we'll look at the first derivative. First derivative had critical values at about 3.87 and 0.13. So if this is, let's say, 0 over here, maybe this is 1, 2, 3, 4. And my critical numbers, 3.87 would be around over here-ish. And 0.13 would be over here-ish. And then I need to test values in between the 3 intervals that these two numbers make. So number to test over here would be what is f prime of 0. And here, what's f prime of 1 would be a nice number. And I guess 4 over here, what's f prime of 4? We just really need to know the sign. If we plug in a 0, so I'm plugging into the first derivative up here, we get 1 over -2 squared, which is positive. So the function should be increasing through here. And what about after that? If we were to plug in a 1 up here, we would get 2 minus 8 plus 1, and the bottom's squared, so it's always positive in the bottom. Right, so the question is, what's the numerator? And I'm going to get 2 minus 8 plus 1, that's definitely negative. You can check on a calculator. So we're decreasing on this side. And at -2, I was or +2 here, right? I was thinking this is a vertical asymptote. We'll double check that with a limit and the graph. And we can't plug in 2. We could plug in 3 just to double check that it stays decreasing even through the asymptote. That's not a bad thing to check. So I'm going to do that just to be careful. f prime of 3, but 2 is not a critical number because the function's not defined there. Critical numbers are candidates for maxes and mins, remember? If we plug in 3, what do we get? 3 squared is 9, times 2 is 18, minus 24, we still get a negative. So the function is decreasing on each side of that asymptote, just close to each side. And then if we plug in 4 up here, we would get 4 squared is 16, that'd be 32, minus 4 times 8 is 32, so we get 1 positive, it is increasing there. All right, so what do we know then? If we're increasing and decreasing, then there must be some kind of max here, so we need to know what is f evaluated at about 0.3. Whatever that is will be the max. 0.313 ain't the max. And over here, we're decreasing then increasing, so f of 3.87-ish is going to be some kind of minimum. And then the question is it relative or absolute? Now, since over here we are increasing and then decreasing, where did we increase from here? So that means there could be lower numbers than that min. And similarly, we have this max over here, but way over here we're increasing. The question is, does this increase forever? So we need to look at some infinite limits next to figure out if these are absolute maxes and mins or local relative maxes or mins. All right, limits. New page. So we need to look at limits of the original function related to infinity and 2. So original function f of x is equal to 2x squared plus x minus 3 divided by x minus 2. And I'm going to do the infinite limits first. So I want to know what is the limit as x. Let's go to the right forever first, positive infinity, 2x squared plus x minus 3. So what is the end behavior on the right side? X minus 2. So our trick here is to divide everything by the highest power of x. And if we do that, highest power of x is x squared, we would get 2x squared plus x minus 3. Each of those is over x squared. Do the same thing in the bottom, and then clean it up. So we have x squared over x squared, that leaves a 2 in the top. X over x squared would be a 1 over x, and then the next one is just 3 over x squared. Down here, we have x over x squared, which is 1 over x, and then we have minus 2 over x squared. And what happens when we do that? Well, the 2 is just a 2, that stays. And otherwise, 1 over x, as x gets big, that gets small. So that goes to 0, that goes to 0, that goes to 0, and that goes to 0. So it looks like in the limit, this looks like 2 over a very small number. Right, so I don't actually get to 0 because I don't actually get to infinity. So this is 2 over a very small number, which is a very big number. So on the right side, as x increases, y increases forever. That means that maximum that I found is a local or relative max, because there are bigger numbers since the function increases forever. So back here, this right here is going to have to be a local or relative, not absolute. And my guess is the same thing's going to happen with the min, that on this side we're going to drop forever. Let's check that limit. What's the limit as x approaches negative infinity? 2x squared plus x minus 3 over x minus 2. Now, same idea as over here. The only catch is that since I have negative numbers here, I'm going to have negative numbers in the denominator down here and essentially 2 in the top. So in the limit, based on the analysis over here, this is going to go to 2 divided by very small negative numbers. So 0 on the left side, which is going to lead me to negative infinity. So that means on this side, y decreases forever. All right, next limit. So we're getting an idea what this function looks like. It decreases forever on one side. There is some maximum value, and then it drops toward an asymptote. So it does something like that. I don't know where the max and min are relative to each other, but I'm going to guess that the min is probably over here. And then on the other side of this asymptote, it goes up there and up there. So far, this is what I'm thinking this function looks like, but I don't know what the max is or what the min is. I haven't calculated those yet. I'll have to do that in a minute. But I just want to double check that this is indeed an asymptote. How do we do that? We have to take the limit as x approaches 2. I'm going to go on the right side first. So I'm going to look at this side first. So this vertical line right here that's kind of jagged is the line x equals 2. 2x squared plus x minus 3 over x minus 2. So if I'm on the right side of 2, that means I'm considering numbers like 2.1 and 2.01 and 2.001 and so on, trying to get close to 2. Now, as I do that, what's going on? Well, the numerator is going to be approaching the value here of when I actually plug in 2, because I'm getting closer and closer to 2 at the top. So if I plugged in 2 to the top, if I cheated, then I would get what? 4 times 2 is 8, plus 2 is 10, minus 3 is 7. So the numerator is approaching 7. What's the denominator doing? Well, 2.001 minus 2, and I keep getting closer and closer to 2, so this difference right here is approaching 0. And since the x value I'm picking is always bigger than 2, then that means this is always greater than 0. So I'm on the positive side of 0 there. So 7 divided by a small positive number is positive infinity. Right, and that's what I was guessing was happening here based on the idea that there was a local min right here. All right, so if I look what's happening on the other side, what if we take the limit as x approaches 2 on the left side for 2x squared plus x minus 3 over x minus 2. So in this case, what does it mean to be on the left side? Well, that would mean checking this value by plugging in numbers like 1.9, 1.99, 1.999, and so on down the road, and looking for the pattern. Now these numbers are approaching 2, so that means the numerator is approaching 7. What's the denominator? Well, my x values are always less than 2, so that means I'm always going to get a negative number, and these two are getting closer and closer, so they're approaching 0, but on the negative side of 0. So I have 7 over a small negative number, which is going to give me an increasingly big negative number. So I'm approaching negative infinity on that side, and that's what I was guessing, because I know the function was increasing on one side of this point and decreasing on the other, and it turns out it does decrease forever, but it doesn't cross this vertical line here at x equals 2. So a function can cross a horizontal asymptote or a slant asymptote, but you can't cross a vertical asymptote because the function's undefined there. All right, so this is roughly what I think it looks like. Next thing I need to do is actually plug in to calculate that local max and that local min. And one more thing, as mentioned earlier, Liam wanted to know about checking slant asymptotes. You get a slant asymptote when the degree of the numerator is 1 more than the degree of the denominator. So let's throw that in before we look at the graph. So new page, this has a slant asymptote. And the only way to find a slant asymptote is to do division. So I need to take x minus 2 into the numerator, 2x squared plus x minus 3, and see what I get. All right, so let's do that. What times x gives me 2x squared? The answer would be 2x. 2x times x minus 2 gives me 2x squared minus 4x. And to next, so it's just like regular division, but with variables. So I guess it's not just like it, but the process is the same. You guess, you multiply, and then you subtract. And the easiest way to subtract is to add the opposite. So change the signs and then add. So the first term should always disappear if you do it right. And then here I have x plus 4x, which is give me a 5x, and then minus 3. All right, so let's see, did I do that right? Yeah, that looks right. What times x gives me 5x? Well, that would be plus 5. 5 times x is 5x, and then times minus 2 is minus 10. All right, and then subtract, change the signs, and we get a remainder of positive 7. So what does this tell me right here? This tells me that my original function, 2x squared plus x minus 3 divided by x minus 2 can also be written as 2x plus 5 plus a remainder of 7 out of x minus 2. So these are both, this is f of x, my original function here. I could also write it as this, and these guys should have exactly the same graph. Now, these two tell me two different things. Like the first one, I can easily see, for example, the y-intercept of it. The second one, if I consider the limit as x increases on the second one, what's going to happen is this remainder fraction here, as x goes to infinity, 7 over a bigger and bigger number is going to go to 0. So that means the end behavior of this graph right here, since that fraction's heading to 0 for big X, that if I zoom out on this, it should look like the line y equals 2x plus 5. So this should be the slant asymptote. So we will graph this and zoom out to see if it does look like 2x plus 5. All right, let's see if all this stuff actually works. Give me one sec. So 2x plus 5, remainder of 7. Desmos time. Okay, so on Desmos, I had started calculating those critical numbers. So I'm going to call this one A, and then the other critical number would be 4 plus the square root of 14 over 2, 3.87. My function, f of x, is a fraction, and 2x squared plus, plus x minus 3 over x minus 2. So here's my function right there. And Desmos is saying it has a max at about 1.29-ish, and the max is, let's click on it, 1.57, right? So here's my critical number, the 1.29. If I plug in what is f of that number I called A, I get a local max of 1.5-ish. And notice I'm missing the rest of the graph. Where is it? Well, it ought to be up here somewhere. Oh, there it is, way up there. All right, so I'm going to change the scale a little bit to see that. Let's see why. Let's go down to maybe negative 5-ish, and then up to maybe 30. That's not bad. Let's go down further. Let's go down to negative 10. That looks better. All right, so let's look at some other things. I believe that there's a vertical asymptote at x equals 2, and that seems feasible here. I'm just going to graph it just to be sure. So if I look up above, I should see the function is getting closer as we rise. The closer x gets to 2 on the right, the farther this climbs, but it can't cross that red line. Same thing down here. All right, so we looked at that idea of the limit to get that vertical asymptote. And I believe there's a slant asymptote of y equals 2x plus 5. And so if I zoom out on this, it should be hard to see the difference between my curve and this line when I zoom out. Now, granted, we have that break in the middle, but let's zoom out here. So when I zoom out, right, my function looks just like the graph of 2x plus 5. You can't see the difference when you zoom out. And that's that idea of end behavior with that slant asymptote. So this function is trapped between these two asymptotes, the vertical asymptote of x equals 2 and the slant asymptote of 2x plus 5. And let's see, I was going to calculate that minimum point. What is f of that number b I calculated earlier? So the relative local minimum is about 16.5-ish right there. And again, that's a local or relative min because there are lower numbers on the curve down here. And I think we've thoroughly analyzed it. And remember, my advice before to you was to explore the derivatives on paper, play a game. Can you look at the calculus of the function and do that analysis to guess what the function is going to look like to confirm on the graph? And then that gets back to ideas like, how does Desmos know that that's the minimum? And there are mathematical techniques like we just applied that confirm that, yeah, the minimum has to be right there. And Desmos uses some of those mathematical techniques. It does it a little bit different than us, but it's similar. Other things to calculate here would be to find the zeros of this function. And remember, we factored the numerator before, which would have given these zeros of negative 1.5 and 1. So we have enough information to accurately depict how this graph has to be shaped.